Okay, so the next speaker of the afternoon is Fosco Loregian, and the title of the talk is Differential to Rigs. And Fosco, you can start whenever you want.
Thanks. Thanks, Ivan. Okay, so first of all, let me thank the organizing committee, but especially the speakers of this conference for the effort they are putting on this, on the organization and on giving these beautiful talks. Okay, so, and thanks for coming also. So, my talk. First of all, I should tell you that this is joint work with Fabrizio Genovese and Todd Trimble. Fabrizio is in Pisa and Todd is at Western Connecticut University. More or less everything I will tell you is based on an archive preprint that Fabrizio and I put on archive on March, and then Todd joined us, and I would say he improved the quality of our work quite a bit. I owe him a lot of he boosted my mathematical maturity in the last 6 months. Okay, so the idea of this paper, that motivated our paper, was very simple. We wanted to study categories that are endowed with an endofunctor that behaves like a derivation. I think all of you is familiar with the definition of a differential ring. A differential ring is a ring endowed with an endofunction that is linear, commutes with sums, and satisfies the Leibniz property. So my motivating question, was to understand better what it means for a category to be endowed with such an endofunctor. And well, first of all, you have to decide which kind of categories you want to study. Fortunately, the very specific flavor of monoidal categories that are the correct object of study were already well understood. They are a fairly well understood, well studied flavor of monoidal category that find applications in algebraic topology or categorical algebra, monoidal categories. They are called bimonoidal categories in original work by Laplace. The idea of putting on them a derivation operation is, as far as I know, new. There are, although, examples of this structure that I believe, I am quite convinced that this approach can unify and can understand better. I find particularly interesting, you will see in a while, that this approach allows also for finding a geometric meaning in a suitable sense behind the structure of a two-rig, the kind of monoidal categories that we will study. You also know very well that there is a geometric meaning in the derivation operation that, for example, in algebraic geometry is encoded by the fact that a certain functor is representable and the representing object is called the object of Cayley differentials. There is a categorical analog of this representability theorem in this setting, which I find extremely cool. One of the main examples that motivated our study was the study of the so-called category of combinatorial species that was introduced by Joyal and gives a very elegant and really neat categorical treatment of many aspects of enumerative combinatorics. So you see, there's a lot of meat on the table already. So let me start by defining you what is the kind of category we are interested in. As I said, the definition of a two-rig, a bimonoidal category, is due to Laplace, who was essentially motivated by giving a clear understanding of coherence conditions that must be true in a category where there are two monoidal structures, one dubbed additive and the other multiplicative, such that the multiplicative structure distributes over the additive one. But we will be absolutely not interested in these coherence issues, and we will instead adopt an extreme simplification, a massive simplification, by asking that the additive structure is always co-Cartesian. So the O plus here is always, for our notion of two rigs, is always given by coproducts. This allows for an extremely clearer and less cumbersome treatment of coherence, as you can imagine. because the comparison maps that witness the fact that x multiplied by 0 makes 0 and multiplication is distributive over sum, here just reduce to the request that x tensor blank commutes with coproducts, with finite coproducts, so in particular with the empty coproduct, the initial object, and the same is true for the other blank tensor x, and this is true for every object x. So let me just mention that this is not the only notion of not at all the only notion of two-rig that you can give. There are different doctrines in the sense of monads, of two-dimensional monad theory, for what a two-rig should be. And actually, in our analysis, we use different choices of what is the doctrine we want to put ourselves in. Because this is what I defined you is a doctrine where the tensor operation, the multiplicative structure commutes with finite coproducts only. You can also ask for this structure to commute with arbitrary coproducts, so of every cardinality, or even with arbitrary colimits. These are dubbed, as you can expect, co-complete two-rigs. And this particular notion was studied by recent work by John Baez and also Trimble again. And so it's quite an interesting notion and also natural to ask. Okay, so now for the definition of a derivation. As I told you, a derivation is just an endofunctor of a two-rig C with the property that partial preserves coproducts, and there is very little to add to this request. And furthermore, it satisfies the Leibniz rule, meaning that this isomorphism is true naturally in A and B for every object. So you see, this is exactly the Leibniz rule. But this second condition deserves at least another minute of explanation, because even though the conditions that I want to put on this map that we chose to call Leibnizator, are quite straightforward, it's a good idea to do this exercise in bookkeeping. So the conditions that this map has to satisfy are compatibility with the rest of the structure, as you can imagine. And the structure is just the multiplicative monoidal structure and the left and right annulators and distributor maps of the two-rig structure. So the way in which these conditions are obtained is completely mechanical, but let me just record them and skim over the diagrams that witness them. First of all, you have a naturality condition, very, very straightforward. Then you ask compatibility with the right distributor. Again, very straightforward. You just ask a certain diagram to commute. The same is true for, of course, on the left for the right distributor. The associator of the multiplicative structure must be compatible with the Leibnizator. So again, and finally, the multiplicative left and right unitors must be compatible with the Leibnizator map. So the only thing which is not straightforward to observe is that this last axiom doesn't imply that the derivative of the monoidal unit, the multiplicative unit, is the initial object, as you might expect if you tried to impose this very well-known and straightforward result from differential algebra. But in a sense, the derivative of the monoidal unit goes as near as it can to be zero, because it is possible and actually quite easy to prove that the derivative of one must be a quotient of the initial object, meaning that the initial map must be an epimorphism. So as you can see, the examples where this doesn't imply that the initial map is an isomorphism are very little and very pathological in a sense. Yet you can construct examples where this map is not an isomorphism, but just an epimorphism. Think, for example, of every poset where being an epimorphism is a vacuous condition. Okay, let me just skim over the fact that there is, of course, a category of two-rigs with two-rig morphisms as their one cells. There is also a category of differential two-rigs, which are those morphisms of two-rig that preserve the derivative operation. a little technical fact that I will need later when I will introduce color differentials is that there is a category of derivations where a morphism of derivation is just a natural transformation between derivations that commute with the Leibniz-Eiter maps on for one derivation and for the other. This is very easy to write down as an equation, as a commutativity condition. Okay, so now let me mention a few examples because I think I convinced you that this definition at least makes a little sense. A couple of edge cases are every Turing can be endowed with the trivial derivation that is just a constant factor at the initial object, and I mentioned posets a moment ago. If you take a distributive lattice, then the identity factor is, by trivial reasons, a derivation, because like this boils down to the fact that every element is idempotent with respect to the sum. So if you write down the Leibniz rule, then you get it almost for free. A less trivial example, which is instead very interesting and very widespread in our analysis, is the one obtained as follows. If you fix a monoidal category, let's take it symmetric just for the sake of simplicity, then the pre-shift category of that, which of course has the property of being the free co-completion, the completion under colimits of A, is a co-complete to rig, meaning that there is a multiplicative structure that is compatible with coproducts and actually with all colimits. Of course, this multiplicative structure is given by Day convolution, which is expressed by this Cohen formula. A very important special case of this construction is when A is free monoidal or free symmetric monoidal on a given category C. And an even more important yet special case of this construction is when C is the point, because in that case, f of 1, the free symmetric monoidal category of 1, is just the category of finite sets and bijections. And the category of presheaves over this is exactly the category of Joyal combinatorial species. This is not by chance. This connection has a true deep meaning because it is possible to prove that this construction behaves like the construction of a free to rig on a category C. So you first take the free monoidal category on that, and then you take the preshift category. Of course, I should say free co-complete to rig. I'm sorry, the co-complete is missing. There is by the way, an extremely interesting and wonderful talk by André about ideas on how to define a notion of free rig on a category. I advise you to check the talk. It was given at a workshop on polynomial functors, and I owe many great ideas for this talk, for this paper to that talk. Okay, in the special case of combinatorial species, this is the form of Day convolution, where you add essentially sum over all the ways to split a certain set, finite set A, as a sum of two elements, and then you mod out for a suitable action of the symmetric groups by shuffling. This is very well known. Okay, let me mention another example. Probably I have to skim very fast over this. Let me just say that there is a way to make precise the idea that you can define a two-rig of polynomials, meaning a two-rig of where the typical object is this formal sum of powers of a certain indeterminate object y. This category, this C of y, is of course a differential two-rig where you essentially perform the same construction that gives you formal derivatives of polynomials. You can extend this construction to formal power series, and this category has a very specific universal property in the category of two-rigs, of differential two-rigs. Let me concentrate instead for this last part of the talk on a more conceptual look on what is a differential two-rig, because I find this theorem quite enlightening and quite motivating for studying this kind of structure. I will just read it to you. There is a bijective correspondence between derivations on a fixed two-rig C and those endofunctors D that are equipped with the left and the right strength in the sense of tensorial strength, with the additional property that the coproduct map of the two strengths is invertible. So if you believe that strong endofunctors or categories equipped with an endofunctor with the tensorial strengths are important, for example, if you like functional programming where these functors are akin or even the same thing as applicative functors, then you must believe that differential two rigs are important, and because they are connected and actually tightly connected with the theory of strong endofunctors. The proof is extremely simple. You just go through the coherence conditions above and inspect them in order to derive the second condition from the Leibniz-Etor axioms. Another extremely interesting result that we found is that if you fix a two-rig and you fix a monoid internal to it, then the derivative of that is a module for that monoid, meaning an object where the monoid is acting. And again, the proof is very simple, surprisingly simple, by inspection of the conditions for being a module. This has, in my opinion, this is related with many phenomena that you see in the wild. Let me just mention that recent work by Obradovich is related to the operation of derivative of an operad in order to obtain something that behaves like a module for that operad. Okay, so let me just skim over the construction of Cayley differentials now. You know that in the setting of algebraic geometry, you get correspondence between derivations over a category and two-rig morphisms between C and let's pretend for a second that C is a ring. Then the quotient of the polynomial ring by the ideal y square is the so-called ring of Cayley differentials. And ring morphisms between C and Cayley differentials are exactly in bijection with derivations. Well, you get the very same result here, the very same isomorphism or equivalence of categories, if you interpret this quotient as a suitable coinverter, meaning that you can define this subcategory of truncated polynomials, and you can show this theorem that there exists a coinverted diagram in the category of two-rigs and two-rigs morphisms that yields exactly the correct object, because if you look at ring morphisms from C to this quotient, then you get exactly a derivation and vice versa. Okay, this is the last slide that I have. There is a lot to say about species. A separate 1 hour long talk wouldn't be enough to cover or even the fundamentals about what are combinatorial species and why they are interesting objects. Let me just say that, as I already told you, the category of species is the category of presheaves over the category of finite sets and bijections. This is a differential to rig under the operation that essentially shifts by one the action of a functor of a presheaf on P. This monoidal structure, even if it's not exactly the coproduct in P, can be seen as the restriction of the coproduct to the core of the category of finite sets. So it has a very precise universal property. This is a very well-behaved example of a differential to rig because the derivative operation has both a left and a right adjoint, and there is a very sleek proof of this that essentially uses this characterization of partial as an internal home in the day convolution monoidal structure. You can provide a conceptual proof of the chain rule with the language that we built that allows, of course, the chain rule was known at the time of when Joyal introduced the notion of combinatorial species, but there are other flavors of categories that behave like species, for example, linear species or colored species, where the chain rule is true and was proved each time by more or less ad hoc arguments. Instead, with this approach, you can see quite evidently that the chain rule is true by formal reasons and always for the same reason. again, another interesting topic is that has a florid field of applications is the study of combinatorial differential equations, meaning that you can think of differential equations endowed with a combinatorial meaning, and vice versa, certain recurrence relations can be characterized as solutions of certain differential equations. There is a huge amount of literature on this subject. This was studied by Joyal and by the Canadian School of Combinatorics that followed the introduction of combinatorial species. So there's a real word out there. Okay. Let me conclude the talk with at least one very interesting open problem that we are in the process of studying right now. You all know and love the theory of polynomial functors, and you all know that it is an extremely interesting problem to characterize initial algebras and terminal coalgebras for polynomial functors. My conjecture, my proposal is to study differential polynomial functors, where you add an additional operation to those that define by induction polynomial functors, which is the derivative of a differential to rig. So what are solutions in this setting? For example, what are terminal coalgebras for differential polynomial functors? This extends and generalizes the theory of polynomial functors in a way that I believe is extremely interesting and can shed a light and provide deeper understanding of many well-known structures. If I have another minute, I can tell you something more. Another very interesting topic to investigate for me, which is very conjectural at the moment, is how far can one push the algebraic theory of two rigs? Because I showed you that one can define quotients of polynomial rings using the machinery, the two-categorical machinery of co-inverters. Is this by chance? Does it work just for polynomial two rigs? Can we talk about quotient two rigs in wider generality? How is this connected with the geometric meaning that colored differentials have in one-ring theory and two-ring theory? So I would really love to understand better these questions, but you know, that's work in progress. Okay, so I'm done. Let me just conclude with the fact that this talk, I want to dedicate this talk to the memory of one of my old professors in Padova, Marco Garuti, who recently, unfortunately, passed away. He was responsible for teaching me differential Galois theory when I was a master's student. So I really see this piece of work as a gift to his memory. Thanks a lot.
So thanks, Fosco, for your talk, and we definitely have time for at least one question. So does someone want to ask something? Yes, we have one question. Give me a second.
Hi, hello, thanks for the talk. I have the obvious question, which is, how does this connect to all the work on differential categories and related notions?
This is a very good question. I still have to understand better that connection. I think my gut feeling, my surface feeling is that the two approaches are actually orthogonal, I would say, because I tried to read through the papers about differential categories, and I couldn't really find any point of connection. Maybe it's me, but that I don't get the core of that approach. They are extremely interesting. Don't get me wrong, and I want to give it another try to try and find a connection between my ideas and theirs. But for the moment, I really feel they are orthogonal approaches. There is just they just share the name differential.
Okay. Do we have
wrong if you? I'd be gladly listening if you want to prove me wrong.
we have other questions? Okay, if not, maybe we thank the speaker one more time.